खासा ब्रेक मिल चुका है, तो वापस से फूरियर की डेफिनेशन और जो रिजल्ट हम लोग ने प्रूव किए थे उसको एक बार रिवाइज करता है. So Fourier transform of any function f of x converted to the variable k. Now what happen is every year I think every question there is different kind of a variable and different kind of a variable to which they want to transform. So ये confusion ना हो, इस चीज का थोड़ा ध्यान रखना चाहिए. I want to find out Fourier of any function that is f of x converted to variable k. We will denote it by capital F of k and the formula was 1 by root 2 pi. So root 2 pi integrating minus infinity to infinity e raised to minus ikx f of x dx. Fourier transform of any function is given by this. If someone knows what is a Fourier transform, तो Fourier inverse to find out Fourier inverse of f of k converted to variable x this time, which is nothing but small f of x, same formula, 1 upon square root of 2 pi integrating from minus infinity to infinity e raised to ikx capital F of k, but this time integrating with respect to the variable k. So the only difference is of plus and minus and we change the variable. अब k से k में हम लोग इंटीग्रेट करेंगे, राइट. सो दिस इज समथिंग इंटरेस्टिंग. इसके ऊपर आई थिंक एक क्वेश्चन हो सकता है आज प्रॉपर्टीज के अंदर. Also we have found the Fourier of two wonderful functions. One of them was e raised to minus ax square converted to variable k, and the Fourier was given by 1 upon root 2a e raised to minus k square upon 4a. And when a is half, sometimes happens, we have considered that case as well. And one more Fourier was e raised to minus a mod x converted to variable k, and the answer was square root of 2 by pi and a upon a square plus a square. So I think these are the things that we have covered in the previous session, and one more property that we have covered. But today we will continue this. Over here, I just want everybody to notice that the two functions that we have considered to find out Fourier, both are even function. Fourier of even function is something special. We are going to study that today. Fourier of an even function, Fourier of an odd function. We are going to consider that scenario today. But today let us just continue with the next thing, that is nothing but properties of Fourier transform. Okay, so we are going to first prove shifting property, that is Fourier of f of x minus a. If x is replaced by x minus a, what will happen to its Fourier? For an example, suppose my Fourier of f of x converted to variable k is nothing but capital F of k. Now I want to see the change of x becoming x minus a. So that is nothing but Fourier of f of x minus a. This is one property that I will prove. Rest of the property I will give time to think. We can discuss it together. So it is nothing but 1 upon root 2 pi integrating minus infinity to infinity e raised to minus ikx f of x minus a dx. So I won't take much time. I'll just say I substituted x minus a is equal to y. At the end, what I get is nothing but f of k, and that would get multiplied with e raised to minus ika. I'll just give 1 minute time to verify whether my answer is right or wrong. Whatever final thing I wrote, just verify it once. I don't know how many. Okay. I think, okay. 3 are there. 4. Just verify the result and कोई है ही नहीं, मंदार अकेला ही आज, ठीक है. Mandar, please verify and let me know in the chat box. If I make that substitution, x minus a is equal to y, ultimately what I get is nothing but the same Fourier, but it would get multiplied with e raised to minus ika. So whenever you have f is replaced by x is replaced by x minus a, you will get the same Fourier as your answer, but it would get multiplied with e raised to minus I k a. Now, one thing that strikes every time my head is how I will remember all these properties, because every year simultaneously they are asking the property. So I suggest never try to remember the property, always remember the basic formula of the transformation, and you can prove this property within few seconds. याद रखने में that makes confusion. Laplace का क्या था, Fourier का क्या था. But this is one of the property of the scalar. Shifting property, form, and then this is a wonderful property. Over here, I want to find out the Fourier of f of minus x whole conjugate. So, by the formula, this is nothing but 1 upon root 2 pi integrating minus infinity to infinity e raised to minus I k x f of minus k conjugate dx. So I've just applied the formula over here. Now what I do is I just take this conjugate to the whole. So this becomes 1 upon root 2 pi integrating minus infinity to infinity e raised to I k x f of minus k whole conjugate dx. So if I take the conjugate, this e raised to minus I k x becomes, changes its sign, and that conjugate I have considered together. Now I use a substitution of minus x is equal to y. Therefore, my minus dx is equal to dy. That is nothing but dx is equal to dy minus. Also, my sign of integration also changes. So it is 1 upon root 2 pi whole bar integrating infinity to minus infinity this time e raised to minus I ky f of y, and dx is replaced by minus dy. This minus sign will change the sign or limits of this integration. So this becomes 1 upon root 2 pi integrating minus infinity to infinity e raised to minus I ky f of y dy and the whole bar. This is actually nothing but this inside the bar. This part is actually nothing but Fourier of my function f. So it is nothing but my f of k, and this is entire bar. So what we are learning, if you are taking Fourier of f of minus x conjugate, the answer is nothing but the same function but with a conjugate sign. So this is nothing but the second property, conjugate property for the Fourier transform. Just see the proof once, Mandar. If you have doubt, you can ask.
So it is Fourier of f of x bar, no?
No, Fourier of f of minus x bar.
We are writing f of capital F of k.
Yes, yes. Okay, yes. This is Fourier of f of x. Correct.
Uh-huh. This is equal to
So okay, what you are telling, I can write over here. If you are finding Fourier of minus x bar converted to variable k, then this is same as Fourier of f of x converted to variable k and the whole bar. This is something that the
yes,
property tells. So if you take the bar outside of that Fourier, that negation introduced, that minus x becomes x.
in the proof, the second line that you used is the property of complex integration.
Yes, what I did is I just took the conjugate together. If I had a conjugate over here, this is nothing but conjugate. This much part is over here.
Uh-huh.
Correct. So
Yes.
that conjugate, I took that together. I took the conjugate outside of the integration because it is a real integration, and then we got the answer. Yes. Is it fine?
Yes.
Okay. So I'll just go for the next property, that is also wonderful property. That means if I have a function, if I multiply it with e raised to I ax, then I don't feel it will take much of a time. This would be nothing but Fourier of k minus a. Within a few seconds, everybody can verify this. Just write the definition. E raised to minus ikx will get multiplied with e raised to iax. Taking ix common with minus sign, what we get as a coefficient is nothing but k minus a. Please verify this. Mandar. Okay. Hmm. We have to find out Fourier of e raised to iax f of x. It is simple. We just have to write the formula and within the next line we get the answer. Yes. So,
Yes,
okay,
yes.
this is interesting. Now what we do, we are just trying to find out Fourier of Fourier again. What we have learned is, if I want to find out Fourier of any function, suppose if it is f of x converted to k, then the formula is 1 upon root 2 pi integrating minus infinity to infinity e raised to minus I k x f of x dx. This is nothing but formula to find out Fourier. And if I want to find out Fourier inverse of some function, suppose it is f of k converted to variable x, then I use a similar formula. The only change is now I will integrate minus infinity to infinity e raised to ikx f of k dk. So over here we have to find out Fourier of Fourier. So let us just see. Over here what I know is my capital F of k is nothing but Fourier transform of small f of x converted to variable k. So let us just see this. This is nothing but by the definition 1 upon root 2 pi integrating minus infinity to infinity e raised to, I want to find out Fourier. So my kernel is nothing but e raised to minus I kx capital F of x dx. Okay. Now what could this? Only data that we have with us is my capital F of x is nothing but Fourier of small f of x. F of k is Fourier of small f of x. We have both the definition with us on the screen. Now what I should do? Hmm. Just think about it once. The answer is actually easy. What would be my answer? Try to use either of this. Either you can use the first one or the second one. Which one is favorable? Just try to use. Hmm. Okay. Let's see together. What I see over here is I know that my f of x is Fourier of something, and this integration I will try to relate it to inverse such that I know the inverse Fourier of this is nothing but small f. So I try to go with the inverse formula. For the inverse, I know my kernel should not have negative sign. So what I do is I write it like this. Integrating minus infinity to infinity e raised to, first of all observe that in this formula I have k that is replaced by x. So it is I x as it is. This k with minus I'll write in the bracket. So minus k. It is capital F of x dx. So observe this carefully. Can I write this formula is actually nothing but Fourier inverse of capital F of x converted to the variable minus k? Can I write it like this? Using the Fourier inverse formula. Yes, Mandar, please observe this and let me know if it is clear. Hmm.
अगर
Ma'am.
थोड़ा परत रिपीट
I'll repeat, ma'am. Okay, so what I did is I was trying to use the Fourier inverse function. because the only data that I have is my capital F is nothing but a Fourier of small f. So if I have this formula, the only way I can find out the answer is to reach till small f, and that is by Fourier inverse. So मैं क्या करता ना मैम, the only thing that I do, I try to change the variable. Okay, so if I change the variable, that would look more easy. Suppose I am changing it like x to capital M. So my variable has changed now. So it is I x m capital F of x, it is dx. So the formula is still same. What I have done is I just changed the variable. So now by using this, let's see, 1 upon root 2 pi integrating minus infinity to infinity e raised to ix as it is, ma'am. What I did is on the place of m, I have minus k. It is f of x dx. Is it okay? Now, can I write this is same as f inverse of capital F of x. Now, on the place of m, I have minus k, right? So, it is converted to the variable minus k.
Yes.
It is fine. So, we know that if my capital F is Fourier of small f, then if I take inverse of this, I will get small f. But this time, the variable is minus k. This is one of the interesting property about Fourier. Why? Because if we know Fourier of something, if you again apply the Fourier, you get the original function, but the only change will be the change in its sign.
Okay.
Correct? So if I have f of x and if I apply the Fourier, I'll get f of capital K. Now suppose if I have f of capital K and I apply the Fourier, then I will get f of minus x. This is that property tells us. If I apply the Fourier, on Fourier, I will get the same function but with the negative sign. Negation of the variable. Okay. We will be using this, I think, somewhere. But this is one of the property of the Fourier that is interesting. And question might be asked. Is it okay? Can we go for the next one? Mandar, is it fine to you? Because you are the only one. Yeah.
Yes.
Okay, okay,
Yes.
okay. Let's see. Then I think these are the two properties that we actually discussed in the last class. So I just kept on the screen, and these are nothing but the list of the properties that we have discussed. This composition is not actually the part of the syllabus. MHSET के syllabus में ये नहीं होता, but MSc के अंदर होता है. This is nothing but convolution. Convolution of Fourier transform. It is defined in a different way, but this is convolution which is not part of syllabus as such for MHSET. But other properties we have discussed. Scaling is something that could be done similar to shifting property. So these are nothing but the list of the property that everybody should know at least before examination. Then we come to the next part, that is nothing but the Fourier of derivatives. Really simple. We have to find out the Fourier of derivative of the function. But over here, we restrict ourselves to those kind of a function which are continuously differentiable, as well as their any order derivative converges to 0 if your x approaches infinity or minus infinity. If your x approaches infinity, the answer of the derivative will be 0. If x approaches minus infinity, the answer of the derivative will be again be 0. What we have to do, we just have to find out Fourier of this derivative. It's literally simple. What I'll do, I'll just try to discuss the first order derivative and I will just let you all think of generalization. So by the formula Fourier transform, it is nothing but 1 upon root 2 pi integrating from minus infinity to infinity e raised to minus ikx f dash of x dx. What we have to do is we have to apply u into v formula. So that is nothing but 1 upon root 2 pi. First as it is, integration of f dash of x would be f of x, and we have to apply the limit, that is nothing but minus infinity to infinity minus integrating minus infinity to infinity derivative of first, that is nothing but e raised to minus ikx. Since we are taking derivative, I will multiply it with minus ik. This times f of x dx. So that is nothing but 1 upon root 2 pi. What would be the first term? This much part, Mandar. Suppose if I substitute the limit minus infinity and plus infinity, what would be my answer? If I substitute the infinity on the place of x on both the times, once I will put infinity, once I will put minus infinity. It won't be f of x. Substitute the limit and see. We have considered a special kind of a function. That is something that I said. We will be working on those kind of a functions which will converge to a zero whenever, yes, whenever the x approaches infinity. So that is a basic requirement that we are considering. So it is 0 minus, now that minus get multiplies that with minus, so it is plus ik integrating minus infinity to infinity e raised to minus ikx. What is left inside is f of x dx. So that is actually same as ik times 1 upon root 2 pi integrating minus infinity to infinity e raised to minus ikx f of x dx. So can I just say this is actually same as ik times Fourier of the function f of x converted to variable k. Right? So Fourier of derivative is actually simple, but the only thing is we have to consider whose nth order derivative will converge towards 0 whenever our variable converges towards infinity or minus infinity. So Fourier of single derivative is nothing but ik times f of f Fourier of f of x converted to variable k. Now the general question arises, what would happen for the second order derivative? I'll just give you 1 minute time, think about it, 1 or 2 minutes, and let me know what would be the generalization. If you get for the second order derivative, what would be the situation if I want to find out the Fourier of f of nth order derivative converted to variable k? What would be the answer? Try to generalize this result. Find out for double derivative and generalize to nth order. Find out Fourier of f of double dash of x. You have to do the similar thing. Yes, anyone? That is ik to the power n Fourier of f of x. Correct? Yes, you could, it could be generalized easily. अगर हम लोग f dash of f double dash of x, if I see f double dash of x is f dash of x whole dash of x like this, it could have been more easier, but it is fine. Taking time is fine for the first time. So this is a wonderful result because many times they ask what is the Fourier of derivative, what is Laplace of derivative. They directly ask the formula, and I think previous to previous year there was a 1 year in which they directly asked the formula. what is Fourier of double derivative of a function. It was so simple. If I want to find out Fourier of double derivative, this thing is actually same as I square. So it is minus the variable square, that is k square, and the Fourier of f of x is nothing but capital F of k. So this is nothing but the answer. Right? So it was ik whole raised to an f of x k. Right? So this is Fourier of derivative. And then the same idea could be generalized if there are multiple variables x and t. But over here we work on the variable x, so we convert x to k. So whenever you take derivative with respect to x, you have to use the same property. Whenever we take the derivative with respect to x, we have to use the same property. But if you are using or you are working with the second variable which is not considered for the transformation, the derivative is applied to the function itself. Over here what we are doing is we are converting this function into, after applying Fourier, this is converted to u kt. So my variable x is converted to variable k. The t stays as it is, that is untouched. So whenever you take derivative with respect to t, that derivative comes outside of the integration and it becomes a derivative. Partial derivative becomes a derivative. Right? So this is nothing but the same property, but in terms of partial derivatives. There are rare situation, I will tell कि I think इतने साल हो गए आज तक कभी भी फूरियर के ऊपर डेरिवेटिव का रिलेशन प्रॉपर्टी पूछा, लेकिन इसके ऊपर कोई सम्स नहीं पूछा उन्होंने. पार्शियल डेरिवेटिव या फिर ऑर्डिनरी डिफरेंशियल इक्वेशन सॉल्व करो बाय यूजिंग फूरियर, उनकी प्रॉपर्टीज जरूर पूछते हैं उन लोग, बट सम्स नहीं पूछे. राइट, सो दिस इज नथिंग बट. Now we come to the most interesting part and the last part of our course on linear algebra. Sorry, linear transformation, integral transformation जो हम लोग कर रहे हैं. Okay, so Fourier, cosines and sine transform. Before I start talking about this, वापस से और एक बार repeat करेंगे formula for the Fourier of f of x converted to variable k. Formula repeat करने के बाद this time we'll try to expand this formula. The formula is nothing but integrating minus infinity to infinity e raised to minus I kx f of x dx. What I know this, my e raised to I theta, by the Euler's equation, e raised to I theta is nothing but cos theta plus I sin theta. So I'm just trying to use that over here. So it is 1 upon root 2 pi integrating minus infinity to infinity. This e raised to minus ikx can be written as cos kx minus I sin kx times f of x dx. So I divide this into two parts now. So it becomes integrating, again it is minus infinity to infinity f of x cos kx minus I times 1 upon root 2 pi integrating minus infinity to infinity f of x sin kx. So this is nothing but actually my Fourier of f of x converted to variable k. We are using this formula from some time now. What we did this time is we have just expanded e raised to I theta. I got one term with cos dx, cos kx and one with sin kx. Now over here we know that my cos is an even function and sin is an odd function. So we are going to make two cases. What will happen if my f, the function of which I want to find out Fourier, if my f is even function, if my f is even function, my Fourier of f of x converted to variable k, if it is an even function, then we can easily observe that this is even, this is even. So this integral minus infinity to infinity becomes 2 times integrating from 0 to infinity. So it is 2 divided by root 2 pi integrating from 0 to infinity f of x cos kx dx. And since if it is an even function, this is even, this is odd, even into odd is odd. So this integration becomes 0. Hence, this is nothing but the answer. That is nothing but root 2 by pi integrating 0 to infinity f of x cos kx dx. And this integration is called Fourier cosine transform of function f of x. So this integration would be called Fourier cosine. What we are observing is my Fourier cosine transform is same as my Fourier transform if the function is an even function. This is an observation based on which last year one of the question was asked. Last to last, I think 2020, one of the question was asked based on this. If a function is an even function, they have asked us to find out the Fourier cosine transform, that is same as the Fourier transform. We will define what is a Fourier cosine in detail, but for now what we did is we just expanded e raised to I theta divided into two parts. First case is nothing but f is even function. We found one of the part is nothing but root of 2 by pi integrating 0 to infinity f of x cos kx dx, and that is nothing but Fourier cosine transform. What will happen if, okay, I will give the time to write, the formula is there on the next slide, but we will consider the second case as well. If my f is odd function, if my f is odd function, what we had actually, I'll just repeat it again. F of x converted to variable k, 1 upon root 2 pi integrating minus infinity to infinity, f of x cos kx dx minus I times 1 upon root 2 pi integrating minus infinity to infinity, f of x sin kx dx. Right? If my f is odd function, this part becomes 0. What is left is nothing but minus I times root 2 by pi integrating 0 to infinity f of x sin kx dx. And this much part is called Fourier sine transform of f of x converted to variable k. So by considering two cases, we got two new types of transformation, integral transformation, Fourier cosine and Fourier sine transformation. They are derived from Fourier transformation only, right? So me just give the formulas. But the only thing why I went for that theory is, otherwise ये formula याद रखना difficult हो जाता है और connection भी अच्छा है. We can use that result once we know how they are connected. So the Fourier cosine is given by root 2 pi integrating 0 to infinity f of x is multiplied with cos kx. Fourier sine, cos kx is replaced by sin kx. And the inverse is as it is. Right? The inverse theory also could be applied, but the inverse transformation is given by the same formula. The only change is the change in the variable. Right? Only changes is the change in the variable. So just note this formula once, Mandar. We are going to use this formula. Okay. If you are done, just let me know in the chat box.
So, Sagar, so total Fourier transform of f of x is equal to cosine Fourier transform minus I times sine Fourier transform.
Minus I times Fourier sine transform. Yes. Is it okay, Mandar? Can we move ahead? Yes. Okay. Let's see. So what we are going to do is we are going to find out the Fourier cosine for some and Fourier sine of some simple transformation. But before we go ahead, I feel it had been too long that we have studied linear transformation. So I just want to revise few things. First is nothing but the formula for the linear Laplace transform. LT मुझे linear transformation ही दिख रहा है आज. It is a Laplace transform. given by the formula integrating 0 to infinity e raised to minus st f of t dt, where real of s was greater than 0. And with that, we have done two more things, important things. Then one was Laplace of cos at is nothing but s upon s square plus a square, where Laplace of sin at is nothing but a upon s square plus a square. Just ऐसे ही याद करने के लिए, let's go for the Fourier cosine of this. Simple function, looks really simple, and it is simple as well. So I know just now we did the formula. The formula is nothing but 2 by pi. I want to find out Fourier cosine, right? So it is integrating 0 to infinity. What I have, my function is nothing but e raised to minus ax. Since it is cosine transform, I need to multiply it with cos. And now the variable is x, which is converted to k. So it is cos xk dx. Okay, so now I just wait for a few seconds. Can you see, Mandar, something that we have already done? Can I see this integration is something special? This integration is something special. I think just to note that down or to point that out, I have yes, yes, this is something that I wanted. We have to change the variable, nothing else. Correct. So what I do, I just write that formula again. Laplace of cos at converted to variable s was nothing but s upon s square plus a square, right? And this was actually nothing but integrating 0 to infinity. What we do now, what will happen is the only change is the variable will change. The formula would be the same. So it is nothing but e raised to minus s t cos a t dt. So we know that this integration is nothing but s upon s square plus a square. Now let us just try to match the things and then we'll see ki kya aana chahiye. Okay. So over here, over here it is t. So the variable t is replaced to x over here, right? And the s is replaced by a. So based on this, first of all, this part is as it is. So s is replaced by a in this case. So over here also my s would be raised by a. So it is a upon a square plus something. This something s is done. This a square. A square. What would be a square? Over here a is replaced by k. So it is k square. K square. Yes. Check it once. Otherwise, I'll mark it with a different color. Where is the green? Okay. So over here I have a. Over here I have a, and the a in this case is replaced by k. So it is this. Is it okay? So this is one of the interesting property. To find out Fourier cosine of something, we are using Laplace of cos ax. Right? Understood, Mandar? The change of the variable. Okay. So now there is one more interesting part in this. As we have seen, the Fourier cosine inverse uses the same formula. You can think of this, whether this equality is true or not. It is actually using the same stuff but in the reverse manner. So I just keep this as an exercise, because once we know Fourier cosine of e raised to minus ax, directly we can talk about Fourier cosine of 1 upon x square plus a square. The only place where everybody might stuck is nothing but the change in the variable. So that is something that need to be considered really careful. थोड़ा अच्छे से उसको देखने की जरूरत है. Otherwise we are using the same thing. So Fourier cosine of e raised to minus ax converted to variable k is nothing but root 2 by pi a upon a square plus k square. And by using this, I am keeping this as an exercise. Fourier cosine of 1 upon x square plus a square. You have to use the same thing. It won't take much time. Now again similar thing. Now same function, but we are going to find out the Fourier sine of it. Let's see. By the formula, this is nothing but root 2 by pi integrating 0 to infinity. The function is e raised to minus ax. Now my variable is x converted to k. So it is xk integrated with respect to x. What we have is, we know that the Laplace of at converted to variable s is given by the formula integrating 0 to infinity e raised to minus st, and I'll multiply it with sine at dt is given by, if I want to find out Laplace of sine at, it is nothing but a upon s square plus a square. Okay, so just think about change in the variable and let me know what I should multiply over here. Uh, Sorry, what is the numerator? The denominator is a square plus k square, that is right. What is should be the numerator? It is k, right? I think you said k. Yes, correct. It is k. So this is nothing but the Fourier sine. Again, similar thing. What we saw over here, similar was was on the previous slide as well. Fourier sine. If you apply the Fourier sine again, what will happen? Right. So I'm just keeping that as an exercise, a small exercise. Okay. So this is an interesting question for which I was running. I want to find out the Fourier sine of e raised to minus ax upon x converted to variable s. So every time we are using different kind of a variable, the only thing that we should remember is the formula, the basic formula. If that is correct, we can always derive the correct answer. Okay. So I want to find out the answer for this. Let us just run for this. This is nothing but the last thing that I am going to discuss. The rest is nothing but the questions which we are actually discussing while we are solving these properties and the simple example. Right? So I want to find out the Fourier sine transform of e raised to minus ax upon x converted to variable s. But just now we have discussed the Fourier sine transform of e raised to minus ax. Suppose if it is converted to variable s, then we have discussed this is nothing but root of 2 by pi. The variable was k previously, now it is s, so it is s upon a square plus s square. We know the Fourier sine of e raised to minus ax is nothing but this. But this time we want the Fourier sine transform of e raised to minus ax upon x. So this is something tricky. One way is to try to think about going through a formula. The next is using this we can move further, and that is nothing but the easiest way. The left hand side is actually root 2 by pi integrating 0 to infinity. I'm just writing the formula for the Fourier sine. E raised to minus ax sine, the variable is x converted to s. I will integrate it with respect to x is equal to root 2 by pi s upon a square plus s square. Now I want divided by x. So what I do is I just integrate, I will integrate both the side. Since I want the division by x, what I do, I just integrate both the side with respect to a, because if I integrate this with respect to a, I have to divide it by minus x. That is an advantage for which we are integrating both the side with respect to a, and it is from the limit a to infinity. So what I have is, I have root 2 by pi. Since it is an independent variable, I can take it inside, integrating a to infinity e raised to minus ax dA sine xs dx is equal to root 2 by pi, integrating that s is constant, so I take it outside, 1 upon a square plus s square, integrating from a to infinity with respect to a, so it is d. Okay, so now it is using a simple integration only, 2 by pi integrating 0 to infinity, integration of e raised to minus ax is nothing but e raised to minus ax divided by the coefficient, that is nothing but minus x. Once we have to substitute a, once we have to substitute infinity, and it is sine k, sorry, xs dx is equal to root 2 by pi s. Now integration of 1 upon a square plus s square dA, it is nothing but tan inverse of a by s, and that should be multiplied with 1 by s. So this s get cancelled, and we have to substitute the limit once a and once infinity on the place of a. Okay, so same thing is over here, on the place of a, once I will substitute infinity, once I will substitute a. If I substitute infinity, it becomes 0. If I substitute a, it stays as it is, so it is nothing but 2 by pi integrating 0 to infinity, minus minus plus हो जाएगा, तो e raised to minus ax upon x sine xs dx is equal to root 2 by pi tan inverse of, once I'll substitute infinity, so infinity minus tan inverse of a by s, right? Is it okay till now, Mandar? All steps are clear? I think मैं बहुत ज़्यादा भागते रहा, मैंने देखा ही. I didn't ask whether it is okay or not. Please go through the step once. If any step you have any doubt, do ask. Hmm. Mm-hmm. हाँ मैम. हेलो. हेलो. इज इट ओके? मेरा आवाज़ जा रहा है कि नहीं पता नहीं. Trying to speak now. I think my network issue is there from my end. uh, हम कुछ तो बोले लेकिन सुनाई नहीं दिया. हेलो हेलो. स्क्रीन शेयर हो रहा है. uh, mm-hmm. Oh, okay. I'll just exit it once then. अच्छा, स्क्रीन ही शेयर होना बंद हो गया. स्क्रीन भी शेयर होना बंद हो गया है. I'll just exit once. Keep those things alive. Stop. Yes, I found it. I think I need to connect it again. Uh, mhm. I think I lost the connection in between. I'll just check it once. Yes. I think I lost the connection in between. I'll just share it again. I think last कुछ part share नहीं हुआ, और मैं कुछ ज़्यादा ही बड़बड़ कर रहा था, वो सुनाई नहीं दिया. I'll just share it again. Hmm. I realized जब reply नहीं आया ना, तब मुझे कुछ लगा कि नहीं, कुछ तो share नहीं करा. कहाँ गया? यहाँ पे होगा. नहीं. ओके. स्क्रीन भी शेयर नहीं हो रहा है. ओके, स्क्रीन शेयर हो रहा है क्या? नहीं. I'm presenting. Yes, I'll just take a minute. Hmm. Oh, let's see the chat box now. ओपनिंग प्रोसेसिंग. कहाँ थे हम? यहाँ पर. ओके. ऑडिबल हो क्या मैं अभी? हेलो 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 हेलो. जस्ट लेट मी नो इन द chat box बंदा. Am I audible? uh, where is that progress? थिंक प्रोग्रेस सब चला गया क्या? सेव नहीं हुआ शायद. Yes, yes, I'm audible now. Okay, so whatever I wrote actually went. It's fine. I'll just write it again. That progress went. It should be there. नहीं नहीं है, चलो ठीक है, कोई नहीं. स्लाइड शो वापस से स्टार्ट करता है, उसी को हम लोग वापस से सॉल्व करता है. सो व्हाट आई डिड इज आई स्टार्टेड विद फूरियर साइन. आई डोंट नो कहाँ से मेरा स्क्रीन शेयरिंग बंद हो गया था. फूरियर साइन ऑफ e raised to minus ax converted to variable s is nothing but root 2 by pi. It was nothing but s upon s square plus a square. फिर हमने क्या किया था, यहां पर इसका फॉर्मूला से यूज कर दिया. सो इट इज नथिंग बट रूट 2 बाई पाई इंटीग्रेटिंग 0 टू इंफिनिटी e raised to minus ax sine transform. So it is sine x is a variable converted to s dx, and that is nothing but root 2 by pi s upon s square plus e square. What we did next is integrating with respect to a from a to infinity. So if I integrate this is nothing but 2 by pi integrating 0 to infinity. The integration of this much part with respect to a from a to infinity is nothing but e raised to minus ax upon x sine k xs dx is equal to root 2 pi. Now integrating this with respect to a, s is a constant, integrating from a to infinity, 1 upon s square plus a square dA. So actually this left hand side is nothing but what is required. So the left hand side is nothing but Fourier sine of e raised to minus ax upon x converted to variable s, and the right hand side is nothing but root 2 by pi s times the integration of this is nothing but tan inverse of a by s, since a was a variable, and that should be multiplied with 1 by s. So this s got cancelled. What we get is this, but we have to substitute a to infinity. So at the last I was writing this is nothing but tan inverse of, once I'll write infinity, minus tan inverse of a by s. Now tan inverse of infinity is nothing but pi minus tan inverse of a by s. After this we use a basic property of tan inverse, that is nothing but tan inverse of m plus tan inverse of 1 by m is nothing but pi by 2. So by using this I can write this is same as root of 2 by pi tan inverse of m plus tan inverse of 1 by m. So tan inverse of a by s plus tan inverse of s by a would be same as pi by 2. So what I got is nothing but s by a pi. I think it is pi by 2. Pi by 4 होना चाहिए था ना. I think I am making mistake. Tan inverse of infinity is pi by 2. So I should have wrote pi by 2 over here. Pi by 2 नहीं लिखा था. Formula is right. Right. So this is nothing but Fourier sine of e raised to minus ax upon x. I don't know. Share हो रहा है ना? Hello, 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 hello. Screen share हो रहा है क्या? I think it again stuck somewhere. Whether it stuck? I need to check. uh, अच्छा शेयर हो रहा है what I think last step तक नहीं दिखा शायद क्या I don't know. I just ended the proof but मुझे ही नहीं दिख रहा है वो proof उसके अंदर see I'll okay, so this is the thing, but the I can see the screen. Okay, Mandar can see. You can see the screen, but is it final answer is written root of 2 pi tan inverse of s by a? Screen is visible, but whether it is updated, that is a question. Is it an updated screen? Yeah, visible. Okay, then it is fine. Okay, okay, okay. It was visible, but it should be updated screen. Okay. Just remove here. Let me just check it once. Huh. I think lag हो रहा है वो because time is not correct. It is lagging because of the network connection, but it is fine. What we ended is we ended with the Fourier sine of e raised to minus ax upon e raised to minus ax upon x. This is something we ended with. Okay. Once we have this much thing in our hand, I think 90% से ज़्यादा portion almost cover हो ही चुका है. Only few minor things might be left. But what we can do is we can discuss some of the previous year question. This is one question that we have already discussed earlier, but let us see a question from I think okay, this is easy. In 2020 they are asking you a basic question on properties of Fourier transform. Just let me know which of the following option is correct in the chat box. F of t minus a. Whenever you have the shifting of minus a, you get the same answer, but it will get multiplied with. So which is the option correct? Which option is correct? Today only we discuss this property. Fourier of t minus a. So option D is correct, right? Actually उनके option के अंदर minus था ही नहीं. We needed to change that option में mistake था. So this D option is correct. E raised to minus ISD will get multiplied. This is 2020 question. 2017 question. What is the Fourier inverse transform of e raised to minus mod of SA? So this is interesting. It might be feasible that we haven't discussed this problem, but it is actually easy. I want to find out Fourier inverse of e raised to minus mod SA. Now, by looking at the option, I realize the variable is nothing but t. So I write t over here. So it is from t s to t. So the formula is 1 upon root 2 pi integrating minus infinity to infinity e raised to uh, option A. Okay, Mandar is right actually. So it is minus se likhna hai. It is IST e raised to minus mod SI. Yes, it is right. The option I should integrate with respect to S. So option A is actually right. Correct? Just check it once. Everybody can take their time. Option A is correct to find out the Fourier inverse. So it is fine. Uh, yes, we can substitute S is equal to minus S and then we can work, it is fine. That won't make more time. So option A is right. 2019. See this is something that I discussed actually. For this problem only I discussed, the answer is nothing but A. Fourier sine transform of e raised to minus at upon t. Now the question might be arise. I didn't discuss this problem because it was asked. I discussed this problem because it was there in the reference book that I am referring. Right. So if you consider any reference book on Fourier transformation, this is one of the standard problems of Fourier sine. There are only few problems which has been solved in reference book. This is one of them. Right? So Fourier sine transform of e raised to minus at upon t is nothing but tan inverse of s by a multiplied with root of 2 by pi. Okay. Just check this and let me know the answer. Fourier transform of second order derivative of this.